of what is sea level rise, how it's being addressed in other countries, and then take you all the way down to what are we doing on the ground, the nuts and bolts adaptation to sea level rise with some local efforts that are going on. So I'm going to introduce each of the speakers one at a time, and then we'll hold questions off to the end after the last speaker. And the panelists will all be sitting up here, and so you can ask questions of us, and hopefully we'll ask questions of each other. So to start off, Mike Furniss is going to kick off this morning's session. Mike's a hydrologist with the U.S. Forest Service, working for the Pacific Southwest and Northwest experimental range stations. He's on special assignment to the Climate Change Office for the Forest Service. And he's just created a climate change resource online website presence as a resource center for information on what the Forest Service is doing. But more importantly, Mike's been traveling all over the world, and he's been interacting with other cohorts in other countries on what are they doing about climate change, how are they adapting to it. And he's been to places as different as Iceland, Mexico, Spain, Vietnam, Thailand, Colombia, Israel, and Taiwan, dealing with this very subject. So he's going to bring the global perspective and what it might mean to us here on Humboldt Bay. So, Mike.
Thank you. I was asked to speak to this topic, and I'll set my timer here so as not to go over. I've got 15 minutes. There is a longer version of this, arguably determinable really on the City of Arcata's website. I have an hour and a quarter version of this lecture. And I'll figure out how this works. So this sea level rise has been called a slow motion flood. You'll notice I've got the words rapid and slow on the same slide there. That's on purpose. It's slow because floods usually happen in a matter of days. We're really talking about decades here. And it's rapid because as far as sea level goes, we're looking at jamming 1,000 years of what would be natural change into 100 years or less. And so time is relative. These are the topics I'll be talking about this morning, some basics, how the changes work, some of the history in deep time or geologic time, and then just touching on what we can do about it. So over the course of Earth's history, large continental ice sheets have advanced and retreated hundreds of times. And each time they advance, they remove water from the ocean and sea level drops. And each time they retreat, that water goes back into the ocean and sea levels rise. And the elevation difference across those natural Earth variations is about 500 feet. And so if this is natural, why are we worried about it? Well, basically because we've put ourselves in the way, ourselves and our infrastructure. And so the water is really what makes the Earth the Earth. There's about 335 million cubic miles of water on the Earth. And it's been about the same amount of water for at least 1 billion, probably 2 or 3 billion years. It never changes. But if you look at how much of it there actually is, that's all of it right there relative to the size of the Earth. And this is how much air there is. So size and volume are relative. And when you think, gee, how could we affect all that? Just look at that graphic there. There's some terms you need to know. This is a global issue. And then the global sea level, which sounds simple, but it's not that simple to define. But this is called eustatic sea level. And then local sea level has a whole another suite of considerations that are very important to figuring out local impacts. And then the isostatic level, the ground elevation, is also important, and sometimes the local sea level is called isostatic sea level. In terms of the controls on the rising of global sea level, there are 2 of them. There's a few others, but the big numbers are just these 2. First of all, the thermal expansion of the water. So as water gets warmer, it takes up more volume. And it's actually quite sensitive to that. And the other one is a melting of glaciers and continental ice sheets. And this first one, thermal expansion of the water, is easy. It's easy to calculate that. It's well known. If the temperature goes up this much, the volume of water goes up this much. The melting of glaciers and continental ice sheets is not at all easy, and it's not very well known. And I'll touch on that a little bit more later. And it's why we have the kind of uncertainty we do about what might happen. Here are some tide records from various places. And what you'll notice is there's kind of a conformance of all of these, except that there's outliers here, Galveston, Texas, and Sitka, Alaska. So what's going on there? Well, Galveston is sinking. It has a severe subsidence problem. There's parts of Galveston that have sunk 10 feet in recent decades. And Sitka, Alaska is rising because it's still responding to all that ice that came off only 10,000 years ago and is rising very quickly. And all the islands of Southeast Alaska will probably outrun any conceivable sea level rise because of this, what's called isostatic rebound. There was so much ice there so recently that it's still kind of rising and relaxing from that ice having come off. And so the critical thing to understand here, and Tom and Roy will talk much more about this, is that the land level changes. In most places, the land level isn't a static thing either, and the land level, of course, affects sea level. If the land goes down, apparent sea level rises. If the land goes up, apparent sea level falls. And they kind of change at about the same magnitude. And so you have to know both of these. So here's the thermal expansion and the melting of terrestrial ice I talked about. And then Tom will talk more about this, that there's various things that affect the level of the land, and you have to know both of these. And these can be very local effects. And I'm sure Tom will drive that home, that it's not one thing, not even in the small area that we're looking at. And then the other thing that happens is these kind of episodic or cyclic things that come in and also affect sea levels, such as tides, storm surge. Storm surge is when there's heavy winds in one direction, it kind of blows a big bulge into the ocean. There's low pressure, the ocean responds to barometric pressure, and so if there's low pressure, the ocean sea level rises. And then, of course, wave height. And then I put in so on, there's lots of other effects here, but I've kind of touched on the major ones here. And so on is one of our kind of, what science types use to try to make things a little bit simpler. If you want to get real complex and comprehensive, then you can't do it. And then if you have storm surge and low pressure, you're likely to have some coastal freshwater flooding as well. And these can all go together to manifest in the local sea level that we worry about. So Earth's natural climate system, of course, has always been changing at a whole variety of scales, all superimposed on each other. But if we look at this, millennium scale, here, this is where the glacials and interglacials, and interglacial is what we're in now, it's not an ice age. These have been changing all through time, kind of on that scale of 100,000 years. So you can think of the glacial, interglacial, and the 500-foot range of sea level rise is kind of the longest wave period there is. And looking kind of at deep time, looking at geologic time, here's looking back 200,000 years. So this is just a little blip in the geologic record, but it's a long time for us. And this is the last interglacial period, and the sea level was 8 to 8.5 meters higher than it is now, just right now in our current interglacial period. And that was about 120,000 years ago. And then we had a glacial maximum at about 20,000 years ago, and then most of the ice was off at about 10,000 years ago. Most of the ice that was going to melt in the interglacial was gone by about 10,000 years ago. And then here's really the big story here, and one that you may not know about, and is just fascinating, really. So again, here's that last glacial maximum at about 20,000 years ago. And again, most of the ice was gone at about 10,000 years. And you can see a very rapid rise in sea level since the last interglacial maximum, or last glacial maximum, rather. And then, what do you notice about this? Look at this. We basically had a stable sea level for the last 6,000 to 7,000 years. And I mean really stable, it really hasn't hardly changed at all. And so we've had this ecosystem service, if you like, of a stable sea level during pretty much all of recorded human history. It's been stable. That changed in about 1910. We started seeing a rise in sea level. And this is, let me go back. Some of these rates here are about 10 times the rate that we see now since that 1910 rise. And there's some very abrupt changes that people that are oceanographers and climate folks that study this believe are meltwater pulses. So large pulses of melting from those continental ice sheets. And then at this point, the Holocene deltas of the world and a lot of other coastal features like Humboldt Bay began to form. This was the origin of this stable period, allowed these large coastal depositional features to form. And so how old is Humboldt Bay? It's about that old. And before that, Humboldt Bay wouldn't have had any water because the sea level was much lower. In fact, at the glacial maximum, we'd have to go out 10 miles or something like that to find the coastline. So this is a big deal here. We've had this stable sea level. We haven't had to deal with rapidly rising sea level in pretty much all of human history, but it appears that that's over now. And there's lots of data that supports this isn't speculative at all. There's lots of reconstructions of sea level. Sea level leaves a lot of evidence, and it can be worked out, and I can show you plot after plot after plot, particularly since the last interglacial. These data are all commensurate. They all fit together, and so we know what has happened. It's also worth noting that there are global heterogeneities in sea level. This is only millimeter scale, and so it's not large, but the situation is kind of worse in the South Pacific than it is here due to changes in currents and salinity and mostly gravity. And so here's the recent sea level rise, and these are not big numbers here, although people that live near the coast in many places have been noticing them. It doesn't take much to actually notice if you live or have your infrastructure very close to sea level. And so the big question is, what's going to happen? How much will it change? And this is not a very satisfying answer. These are the projections. This is IPCC 8/4, which is was the big splash publication for climate change. And then this is a number of other credible authors who have predicted various things. And you see an awfully big range here.
What's the axis on the left, Mike?
I'm sorry, that's centimeters.
Thank you.
So this would be 2 meters here. And so IPCC projected basically less than a meter, and a number of other authors are saying it would be prudent to consider 2 meters is what we'll see, and there's a big range in there. Here's another set of projections. And the interesting thing about this is we're looking over 100 years, although that things will continue to change beyond 2100. But really, all we ever look at is out to 2100, and that's further than we're used to looking. But this time period and the magnitude of the change is human. It's about a human time scale and about a human stature, which is kind of interesting. So here's the big wild card. Is the melting of continental ice is not well understood. So there's been glaciologists and glaciology for a long time, but not very many. And the continental ice sheets were not melting, and so nobody really worked on this. There wasn't really a scientific study of how did the continental ice sheets melt up until recently. There's a ton of work on it now, but it's not well understood. And there's a lot of complex dynamics, particularly at the base of the ice sheets, and then the runoff from the top of the ice sheets that really complicate the picture. And so the degree to which we understand how this will be affected by a rapidly warming climate is not well understood, and is the subject of a great deal of debate. When IPCC released AR4, they couldn't agree on how this would play out, so they left it completely out. And so the only thing that is in that publication is thermal expansion, and that's why that number is so small. It now appears in reconstructions of the previous interglacial period that thermal expansion can only account for a relatively minor or smaller part of sea level than melting of continental ice. So this is the big wild card, And it's why you are not going to get a good answer about how much will sea level rise by X time. It's just not something you can get out of science right now. And it's also become clear that the change can be very abrupt and rapid, so it can happen quite fast. And just an illustration of how changes in average affect changes in extremes. The extremes really run things, and that's when the impacts really happen. Here's the extremes, and then if you just add sea level rise to it, is something like this. It's not always that simple or additive, but that gives you the basic idea. Here's another one. Here's the wave height at 100-year flood elevation, and if you add sea level rise to that, it's just up a little higher. Here's how this inundation without flooding plays out in San Francisco area. This is one of the most vulnerable places in the West Coast. And you can see there's lots of areas that kind of go underwater. This shows a 1 meter sea level rise. And the Pacific Institute and Scripps and USGS have come up with some projections for California. And so this is probably the best data we're dealing with. And this is I think the 55 inches that people are using for 2100. I think that's still, you have to realize that that's still quite uncertain, and there could be big surprises because of that uncertainty about the melting of the continental ice sheets, Greenland and Antarctica. And just taking a quick tour about how this plays out in different parts of the world. You can see, obviously, Denmark and Belgium. This in England, on the east coast of England. These are those big Holocene deltas right here, and they're the ones that, because they're young, they're close to sea level, and they're subject to inundation. Again, Holocene deltas, the Amazon and the Orinoco, lots of people live here, and they're very vulnerable. Here's Alaska, the Yukon. A fair number of people live here, but it's nothing like the large deltas. And then the Mackenzie. The copper doesn't change much because the whole place got jacked up 10 to 30 feet in the 64 earthquake. Okay, and then this is probably the most vulnerable place in the world. Here's the Mekong Delta in Vietnam. And you can see Indonesia and New Guinea have some very severe impacts. This is Thailand here, so southern Thailand is a very problematic area. And just an example, there's a joint US-Vietnam working group on climate change, and I've been representing the US in that. And boy, they're rolling up their sleeves over there and trying to figure out how to deal with this. They're actually not having any debate about whether it's real or not. Their political class is engineers and scientists, interestingly. But anyway, this is just 24 centimeters of sea level rise with a 30-year flood. This is the Mekong Delta here, and this is Ho Chi Minh City and the former Saigon, and the whole thing goes underwater. So yeah, they're really worried. This is Bangkok, which is built on a delta. And Bangkok has been sinking for many years because of groundwater withdrawal and the weight of the infrastructure, and sea level rise makes it much worse. This is our Mississippi Delta, and New Orleans here obviously was highly vulnerable without sea level rise, and we saw the consequences of that. Sea level rise makes it more vulnerable yet. And there's a number of places in the world we could say are going to be in the same kind of vulnerability situation that New Orleans has been in for a long time. We have a fairly vivid demonstration of what can happen when an extreme event comes by in a vulnerable place like that. The bulk of the population, this is what happens in the Middle East. This is the most vulnerable area in the Middle East, is Egypt. The bulk of the population of Egypt lives on the Nile Delta. And this is again one of those Holocene deltas that formed in the last 6,000 years. And this is the area that's subject to flooding in basically a rare coastal flood event with sea level rise. Of course, this area where the Ganges and the Brahmaputra River come together, Bangladesh, is also highly vulnerable. Lots of people live there. And then the Gulf Coast and the eastern seaboard and the Yucatan Peninsula are the most vulnerable areas in the US. They're very low-lying, And obviously, we've seen what can happen in the Gulf Coast, even without much in the way of sea level rise. But all this eastern seaboard here, and of course Florida, are highly vulnerable. And that's where most of the work is going on right now in terms of developing modeling systems and adaptation methods. So what happens here, I won't spend much time on this, I'm sure some of the other speakers will get into this more. We didn't build much out on the Spitz, fortunately. There's very little infrastructure out there. But the bay is part of the ocean system, and we do have a lot of infrastructure on the bay. And this is some modeling that was done by the Pacific Institute and Scripps, looking at the 100-year high water event. So the high water event that has a 1% chance of happening in any given year, plus particular amounts of sea level rise. And the yellow is that 55 inches. That's from kind of a standard of analysis in California. Here's another Pacific Institute one, and looking at Eureka. And then zooming into where we are now, let's see, we're right about in here. It was already in the flood prone area, and I'm sure that was considered when this was built. It seemed like we're way up on a high point here. But sea level rise is this blue section here that's added to that, and it gets considerably worse. And Arcata's a little bit gnarlier than Eureka because of its general elevation, and there are places where the vulnerability is really very high in Arcata. This is just inundation without a flood, but just showing that the Eel River Delta will, and again, this is a Holocene Delta, will be flooded. And then the San Joaquin Delta, also at 1 meter sea level rise, is largely flooded, and adds a whole other level of complexity to an already fabulously complex place. And then to finish up, I'll just touch quickly on so what's the problem with this? And the problem that occurs first is saltwater intrusion, usually, is saltwater intrusion into your freshwater supplies. If your freshwater gets salty, it's time to move or find some other freshwater, which can be very hard to do. This is the Mekong Delta, and people live like this here, and if this water goes salty, it really changes their situation big time. And incursion 30 years ago into the Mekong Delta was about 10 kilometers, is as far in as the salt influence would come episodically, and now it goes about 40 kilometers into the Delta. And they're trying hard to adapt to that. There is a professor who's going around and documenting how Vietnamese people that live in these areas are actually adapting and coming up with some fabulous creative solutions. Very adaptable people. And then what really makes it real, this is just pictures of New Orleans, but what really makes sea level rise come home, I think, is what we call the perfect storm. I already alluded to it before, but if you have one of these especially high tides, we call it a king tide, or the formal term is a perigee spring tide, where you have the moon in its elliptical orbit is closest to the Earth, and the moon and the Earth are lined up. Then you have the highest of the high tides. It happens 2 or 3 times a year. And if that corresponds with low barometric pressure and storm surge, and then maybe some freshwater flooding, then the ocean comes into your front door. That's when it really becomes real. You may not notice it until you have this kind of unusual but entirely credible and predictable, not predictable, but anticipatable confluence of events that it really becomes real. And I won't go through this, but there's lots that can be done. We have lots of experience in dealing with coastal environments. Coastal environments are super dynamic, and infrastructure is not dynamic at all. And so we've got all kinds of ways of dealing with this, and we'll probably find a lot more as we deal with this in the future.